Let's talk about radioactivity and half-life in this video. Radioactivity, which is also called radioactive decay, refers to the spontaneous emission of rays or particles from unstable isotopes or radioisotopes. These rays or particles are called alpha particles, beta particles, and gamma rays. I am assuming that you know the differences between these particles and rays. Atoms of these isotopes become stable when changes occur in their nuclei. Carbon-14, for example, releases beta particles to become nitrogen-14, which is a stable isotope. Not all has the same simple path, unfortunately. Lead-210, for example, releases beta particles and gamma rays to become bismuth-210, but this isotope is still unstable. So, it releases beta particles to become polonium-210, which is also unstable. Since it is still unstable, it will release nuclear radiation, this time in the form of alpha particles to become lead-206, which is a stable isotope. And these processes take a lot of time. Speaking of time, let's talk about half-life. Half-life is the time required for one half of the nuclei in a radioisotope sample to decay to products. Half-life varies for different isotopes. Sometimes it takes billions of years to happen, while sometimes some isotopes decay in seconds or in minutes. After each half-life, half of the original radioactive atoms have decayed into atoms of a new element. Say for example, we have 100 kg sample of carbon-14. Carbon-14 has a half-life of 5,730 years. So after 5,730 years, our 100 kg sample of carbon-14 becomes 50 kilograms and the other half becomes new element through the process of radioactivity. It follows as well that after another 5,730 years, the remaining 50 kilograms of carbon-14 becomes 25 kilograms and will become 12.5 kilograms after another 5,730 years, and so on and so forth. This idea can lead us to some common problem-solving activities involving half-life. Let's try this one. Carbon-14 emits radiation and decays with a half-life of 5,730 years. Assume that you start with a mass of 300 grams of carbon-14. How many grams of this isotope will be left after 17,190 years? First, we identify the given. We have the half-life of carbon-14 to be 5,730 years. The initial amount, 300 grams. The time or period is 17,190 years. You can solve this problem probably using simple mathematical processes. Since we have 300 grams initially, after 5,730 years, we will be left with 150 grams. After another 5,730 years, we have 75 grams of carbon-14. We can continue this process until we complete a period of 17,190 years. So, we add another 5,730 years and we'll be left with 37.5 grams of carbon-14. This is the remaining amount of carbon-14 after 17,190 years. This process seems very effective, but if you will be dealing with lots of numbers of half-lives, then it will be very complex and time-consuming. So, we can use this exponential decay function equation to help us in our calculations. A is equal to A sub naught times 1/2 raised to n, where A is the remaining amount, A sub naught is the initial amount, and n is the number of half-lives. We can compute n by dividing the period over the half-life. So in our example, A sub naught is 300 grams times 1/2 raised to the period, which is 17,910 years, divided by the half-life, which is 5,730 years. Simplifying that, we see that n is equal to 3, which is the number of half-lives in this example. So finally, we can get the remaining amount of carbon-14 after 17,190 years, which is 37.5 grams, exactly the same as our first method. Now, what if we are asked to solve for the half-life? Let's say you start with 200 grams of isotope X. After 20 minutes, 12.5 grams of isotope X is left. What is the half-life of this isotope? So here, A sub naught is 200 grams The period is 20 minutes. The remaining amount after nuclear decay is 12.5 grams. We are asked to find for the half-life. Well, you can still use simple mathematical steps, but since we have the formula already, we'll take advantage of that. So, A is equal to A sub naught times 1/2 raised to n. We can replace n since n is period over half-life. Plugging all the given, we will have 12.5 grams is equal to 200 grams times 1/2 raised to 20 minutes over the half-life. Rearranging and simplifying will end up with 0.5 raised to 20 minutes over half-life. This is equal to 0.0625. Now, we need to use some logarithm rules. For example, 3 raised to 2, which is equal to 9. In logarithmic form, this is the same as log base 3 of 9 equals to 2. We use the same idea in our solution, so we have log base 0.5 of 0.0625 is equal to 20 minutes over the half-life. Log base 0.5 of 0.0625 is equal to 4. So finally, we can solve for the half-life, which is equal to 5 minutes. Do some practices and I'll see you again next time. Keep solving!